All right, silly people, here's the situation. We're going to be calculating a derivative computationally um, using just the definition of a derivative from like calculus 1, where df dx is equal to f of x plus delta plus f of x divided by delta. And actually, it should be the limit of that as delta becomes small. So let me actually do limit underscore delta right arrow 0. That looks a lot better. But yeah, that's the definition of a derivative. And we're going to be testing that formula pretty much, just taking a really small value for delta and testing it against this function here, x minus 1 times x, which we know that the derivative of that is just 2x minus 1 analytically. And so if you plug in 1 for that, you should get out 1. When we do the computational method, it's going to give out a value that's not quite 1. It's going to be off by a bit. So first of all, write a program that defines the function f of x. So that's easy. F of x, it's going to return x times x minus 1. And then we just do the derivative df dx with delta equal to 10 to the minus 2, so 1e minus 2. It'll be f of x. And actually, we're plugging in 1 for x, so it's going to be 1 minus, or 1 plus delta minus f of delta. No, just 1. Yeah. But then you divide the whole thing by delta, is what you do. So all divided by delta, and we'll have it print df dx. And we'll see what we get. Okay, got 1.01. So our answer should be 1, but it's off by a factor of delta, looks like, which is interesting. So that's just because we calculated with such a large value for delta, it's going to be off. If you do it on paper, you'll get a similar result if you do it just like that. But part B, we're going to have to repeat the calculation for a bunch of different deltas, basically all negative powers of 10, increasing by 2 for each one. So what I'm going to do is I'm going to use this same code here, and then put it in a for loop. So instead of having a fixed value for delta, we're going to do for delta in a list that we're going to define explicitly as just 1e to the minus 2, 1e minus 4, 1e minus 6, 1e minus 8, 1e minus 10, 1e minus 12, and 1e minus 14, right? And then it's going to calculate a value for the derivative for each of those deltas. And for the print line, for clarity, let's give it some text and be like delta equals, and then it prints out what the value for delta is after a space. And then we'll also have it print out df divided by dx, and then it'll print out our value df dx, which we calculated for each delta. And so that should do it. Interesting that it didn't print that in scientific notation, but whatever. So it looks like it got 1.01 again for the 0.01 case. Then it's off by delta again here, and it's off by delta again even there. And the most accurate it gets is around delta equals 1 times 10 to the minus 8. But then it starts getting less accurate again, because now it's jumping back up, and it gets even less accurate when you have 1e to the minus 12, and then 1e to the minus 14 is right off. Why does it just get worse once you go past a certain value of like how small it is? Um, Again, it has to do with the fact that you're subtracting numbers that are very, very close together. Whenever you get to delta equals like 1 to the minus 10, or 10 to the minus 10, I guess, the difference between f1 plus delta and f of 1 is so small that you're going to get like flow errors in between. But like, yeah, it's going to get worse, and there's not really anything you can do about it for now. All right.